Hello, everyone. So my name's Marc Baldo. I'd like to introduce some work on organic LEDs. This work is in two parts. Part of it, the synthetic part, is I'm obliged to my colleague John Lee at Arizona State for providing some of the blue materials. All right, so I think it's more than 25 years since phosphorescence, which is a high efficiency OLED technology, was introduced. And at this point, of course, red and green has been very successful, at least in small displays. But I want to focus on blue, which remains something of a problem. Now, in the last 25 years, there's been, of course, an enormous amount of money spent and work conducted to try to solve this. And that has mostly followed the same path that was taken to stabilize red and green, which is let's synthesize lots of materials, let's try them out, let's see what works and what doesn't. That's not necessarily a good fit for us to do that kind of work. So instead, what we're doing is trying to understand what's happening in blue OLEDs and then try to propose some device structure solutions. All right, so I want to talk about two things today. First is, I think, some very interesting results that we're going to show for the first time on what's happening inside high-efficiency blue OLEDs. Of course, one of the problems with OLEDs is they tend to be a bit of a black box. It's very difficult to know what all the dynamics inside are. There's all these different species and they're all interacting in different ways. And how do you disentangle what's going on so that you can figure out what to work on? And then I want to talk about one of the topics that's been current in blue OLEDs recently, which is this idea of speeding up light emission for better stability. All right, so let's talk about this first. All right, so I think about an OLED as a machine that basically makes excited states. Of course, OLEDs are not made out of very conductive materials. You make them very thin and you put a whole lot of current in and hopefully you form some excited states in there. What this means is inside the OLED, there's an awful lot of energy stored in these excited states, which is what we're fundamentally fighting against when we try to stabilize them. So the conventional wisdom in the field is that this stored energy can interact within the OLED and you can get these kind of bimolecular processes which are correlated with degradation. And of course, this is the other reason why OLEDs have a very hard time at high brightness, because as you increase the brightness, you get more and more of these bimolecular things. They kind of increase quadratically or even faster, and that causes an issue at high brightness. So one is the interaction between so-called triplet excited states, which are the long-lived spin 1 excited states, and the other is the interaction, so they can either interact with charge or they can interact with each other. And it's thought that these lead to damage. So one of the interesting things that we've been pursuing is both of these phenomena, the interaction between triplets and charges and the interactions between triplets and triplets, are both dependent on magnetic fields. So in general, the magnetic field doesn't really do anything to the OLED, except it narrowly focuses on these two rates that are thought to be very heavily involved in degradation. So it's an interesting experiment to do, is like, what does it do? So first of all, I'm not going to go into the quantum mechanics of this. We don't have time for it really, but I'm happy to discuss it afterwards. But you can think about the magnetic field in all cases as basically slowing these processes down. It takes this jumble of excited states and then splits them all up according to the field. And because the excited states are now all different, some of the pathways get stopped. And so, for example, this process slows down under a magnetic field, and this process also slows down under a magnetic field. But there's a couple of questions. First of all is like, how big does the field have to be? Remember, we've got platinum and iridium and all kinds of like things that mix up the spin states inside the OLED. And the second thing is, okay, that's an interesting thought, but what is going to happen to degradation? So I'm going to skip over a lot of work and show you some interesting data here. So this is a blue OLED. What we're looking at here in the orange is this thing degrading. It's an okay for academia, I think, OLED. And what's notable though is that, first of all, at low magnetic fields actually it doesn't really do anything to the degradation. It's like almost negligible. So down here, if you're like at 0.4 Tesla, there's no real change in the slope. You can see a change in the overall brightness. That change in the brightness is because we're reducing the quenching from this triplet charge interaction. We turn it off. And so it gets like a few percent or less brighter. So anyway, down at low fields, nothing really is happening. But at high fields, oh my goodness, there's something crazy happening inside this OLED. Like it's really, really complicated but it's a very big change. So if you zoom in on that, what you can see, so let's just look at this region where we're putting 1.5 Tesla on. I don't think anyone's ever done this before with an OLED, which is maybe one of the reasons why it's interesting. If you look there, you can see this is the degradation rate prior to the magnetic field. Then you put the magnetic field on, you see this increase because we've turned off some of the losses. And then we have this weird peak, which is very slow. This is happening over 5 minutes or so. And then the loss rate picks up again, and it's now 3 times faster than it was before. Very, very interesting, I think. So what do we think is going on here? So there's this idea in OLEDs that the triplets and the charges interact and it's bad, but I'm not entirely sure that's completely right. I think if that was true, then what we would have seen is the OLED would have got a lot more stable under the magnetic field, which is actually what we thought would happen. So at least what I thought would happen. So what we think is going on is normally if these triplets are around a charge, they can just give their energy to the charge, it makes that charge hot and then it decays away, it just kills the energy. But we think that in some cases, that process, although it's bad for the efficiency of the OLED, actually helps protect the OLED against damage. It takes these excited states and kills them, and they can no longer cause degradation. Now, if you put it under a magnetic field, however, you lock some of these processes, some of these interactions out. They're spin forbidden. And so we think it's now possible for this much slower background process, which is killing the OLED, to emerge in a much stronger way. So we think that we're very specifically targeting these kinds of interactions in the OLED. Second thing is, when we get into this in more detail, which we're working on in this program, we think it's very likely that the magnetic field dependence, so basically, why do we see this at 1.5 Tesla instead of at 0.4? That's going to tell us what, in fact, is the reactive species inside the LED. So that's just sort of a hint of some of the current work that we're working on. But I also wanted to talk a little bit about, at the device level, what's happening in blue OLEDs and how to make it more efficient, more stable and more efficient. So that's this idea of speeding the thing up. So basically, why do we think this is an important issue? So if we want to sort of think about a primitive kinetic model of the OLED, what we think is, okay, there's some energy, it interacts in some way inside the OLED, it forms a defect, and maybe that process goes as the square of the exciton density on lifetime. Once we have a defect, then we get quenching after that, and that again goes like the exciton lifetime. And so it's possible that this thing could go like the cubic power of the exciton lifetime. So the exciton lifetime should be a very powerful way to influence this. And in fact, a while back in collaboration with UDC, after we proposed this idea, we showed that at least optically we were getting these gigantic dependencies of stability on exciton lifetime. Now that's photostability. But we saw it in green, we saw it in blue. It looked really interesting. And after that, so that was the original patent of this work. After that, our collaborators at UDC went ahead and made devices, and also Steve Forrest at Michigan also made devices. And they saw big effects, power laws about 2.3, both at UDC, and also power laws at 2.3 at Michigan. We didn't publish anything because we couldn't get this effect. So we'd proposed it, that it should work, and we'd seen it in optical films, but actually when we made OLEDs, we didn't see it. And so I want to talk about that. It was slightly frustrating to watch some of this in the field. So the device structure that we're going to use is the archetype here is the Samsung blue phosphorescent OLED that was published in Nature Photonics a couple of years ago. I'm not going to go into any details here. It's, I think, exactly the same structure and same materials. And we changed the cavity, we changed the light extraction properties of the cathode to look at a fast, medium, and slow device. So all we're doing here is altering how quickly the exciton goes to light emission. IV's all the same. These are the transient PL showing that we are, in fact, modulating the speed. And let's just quickly get to the results. So what we saw, first of all, this is the EQE roll-off, basically the droop as this thing goes to higher current density. So the slow, medium, fast, it does get better as you speed it up, as you would expect. Here's the lifetimes that we saw from slow, medium, fast. Basically, well, what's interesting about this is it doesn't really do very much, at least when we were doing it. So although our colleagues saw these power laws of 2.5, so by the time they've changed the lifetime by the factor of 2, we should have seen like 4 or 5 times improvements in stability, but we didn't. And so here, I'm actually plotting these power laws. In the roll-off, we saw a power law of 0.37. In the LT90, the stability, we saw a power law of, a half. So very kind of bad. And we're like, why? Why is this? And so I don't have too much time. I'm happy to talk about this afterwards. But basically, we think what's going inside the OLED is that there's another species. And we can, again, see it with the magnetic field. But the conventional model of an OLED doesn't include it. So typically, what you think about the OLED is you put in charge, it makes these excited states, and those excited states emit light. Well, sometimes they quench each other, but mostly they emit light. and this, I'm at least partly responsible for this model of an OLED. It's like worked really well over the years. But when we modulate this, it doesn't work. So we think what's going on is that in fact there's a bunch of other states that are in the host and blocking layers that are dark and not modulated by things like what we're doing and the cavity effects. And these sometimes transfer over here, but sometimes they don't. Sometimes they annihilate and sometimes they cause degradation. And so the dark triplets are really important. And you can look at them with the magnetic field. These guys, it's specific to these guys. The other thing you can do is you can put an exaplex host in which kills these things off. So just going through that, indeed, if you start considering these other states that we propose exist, the so-called dark triplets in the host material, you can then start to explain what's happening in the device. So we have another whole shadow set of bimolecular interactions that we propose exist. And then you can start to explain, indeed, that's why the roll-off looks the way it does. And if you kill it off by putting in a so-called exaplex host, again, the Samsung OLED did this also. So we put in another host material which kills those states. Then we see this magnetic field dependence, which is seen, which shows these dark triplets. This is their magnetic field signature. That disappears in the exaplex host. And suddenly, along with that, the device starts working better. You get a better dependence on exciton lifetime in the efficiency, and you get a better dependence on exciton lifetime in the stability as well. So it works a lot better, almost twice as good. So, that's really not visible. So anyway, the main point here is, I don't know if you can see that, the slope here went from 0.37 to 0.68 in this efficiency, and then in the stability, the slope has gone from -0.5 to almost 1. So these dark states are very important in OLEDs, and I think in your blue devices, you may very well have them. We certainly did in some of these devices, which were made from the Samsung recipe, essentially. But we're still a lot worse than what other people have seen, like UDC and Michigan in particular. So I can speculate about that afterwards. So just to summarize, I think the inside of a blue phosphorescent OLED is a very complicated thing, but we are starting to develop probes that will tell us what's happening inside those OLEDs, and to be able to distinguish the exact chemical species that are interacting and causing trouble. Nevertheless, we still have very complex things, and the simple model of OLEDs is not working, I think, on explaining why the blue phosphorescence is doing what it's doing. And I think to ensure that we get the best performance out of things like light extraction, fast light extraction, we need to eliminate some of these dark states like the dark triplets. So let me just wrap up then. I think what we're looking at is some of these things. We're trying to be a bit more specific and a bit more scientific about phenomena that the OLED people have talked about for years, like unbalanced charges and recombination zone movements. I think these things are actually microscopically forming excited states in places that we don't want those excited states to form. And we're going to work very hard on expanding out our in situ magnetic field studies to do measurements on actual OLEDs as built, particularly in the industry. All right, so with that, I'd like to thank the people that did the work. This is Jan Tippelt, who's graduated now but did the original work on the dark triplets. And this is Oliver and Zhong Wong, they're both here, supported under this program. Thank you.
Thank you. Very nice talk. Very interesting, yeah, photophysics of the system. So for the first portion of the talk, you talked about the impact of the magnetic field, right? And then I guess the hypothesis here was that maybe the triplet a channel becomes less efficient, and then other things that are not affected by it, right, can take over. But since it seems like the degradation processes that are at play are charge transfer based, is it possible the electromagnetic field also changes something like the dielectric of the media and then become also more efficient, so you're actually affecting everything really?
Yeah, it's a good question. So I think maybe to summarize is, how do we know the magnetic field is not influencing everything else, especially charge transport in the system? So at least to the best of our knowledge, and we need to do more work on this, none of the sort of traditional spin transport phenomena are really very active in this system. We don't have magnetic contacts. The electrons are sort of hopping very slowly. The carrier velocity is very low, so we're not expecting kind of Hall effect type stuff. And as best we can tell, the strongest impact is coming in at the exciton level. The exciton and charge interaction looks like it's the most dependent on the magnetic field. But of course, you're right. We need to verify, and we do see changes, in fact, in the conductivity of this OLED. So there is something that's feeding into the electrical part, which is something we'd be happy to talk about next time. But at least our current hypothesis, let me frame it that way, is that the lead initiating event in all of this has got to do with the exciton interactions. But it's a good question.
Thank you.
Yep. Okay, so let's move on to the speaker. Thank you, Marc.